So far in our study of first-order systems, we've focused on this equation here, or this standard form, which is the homogeneous form of a first-order system. However, as we'll see in later applications and have reason to believe from previous applications, we might also need to be able to handle some kind of non-homogeneous element to this, something that isn't represented as x related to x, but maybe an external force that is being applied or external stimulus is being applied. It would show up in the equation in this location here in standard form. If we do get this in an equation, what are we going to do? Well, we have a method that we've used before, just like we recycled our exponential assumption solution to get the solution to the homogeneous part. When we solve for the f of t, we're going to look for the solution using the method of undetermined coefficients. And all that method was finding the differential family of, in this case here, it's f of t, and that differential family is a set of functions. So a set of building blocks, linearly independent building blocks, that can be combined to make f of t. So I'm going to call them f1, f2, and so on. And it might be, who knows, could be one function, could be many, we don't know. Depends on what f is. Completely irrelevant what is in this side here. It's all about what's in f. From there, we can build the proposed solution. And it'll have the same idea or same form as we had before. It'll be the non-homogeneous solution. It'll involve our functions, f1 of t, but these are going to be scalars. And we need to have a solution that's a vector. So the way we get around that is we have a vector of constants, u1. Then we'll have f2 of t times u2, plus f3 of t times u3, plus however many more of those we need. I'll call it m, um. And so these u's are the undetermined coefficients. They are the things that we don't know, but we do know that we have these functions that will be required when we sub in for x to cancel out the non-homogeneous part of the equation. As an example, let's consider this differential equation here, which is non-homogeneous. We can tell at a glance because of the presence of this extra term added on to the x term. And you notice there's no way to put this inside because there's no x1 or x2s in this term. So an equation is either non-homogeneous or it's homogeneous. It can't be on the fence between the two. We'll save some time by looking at A and pre-calculating the eigenvalues and eigenvectors. And when we do that, we can immediately write the solution to the corresponding homogeneous part, which is this. This is the corresponding homogeneous version. And it has a solution that is some constant c1, e to the lambda 1, which is 5, e to the 5t, times the vector here, 7, 1, plus c2, e, second eigenvalue, negative 1t, times the second eigenvector, 1, 1. So if we have the matrix, and we can go immediately to the eigenvalues and eigenvectors, we can write down the solution to that. We're now going to focus our attention on this non-homogeneous part. And we notice that the differential family here is simply the set e to the 2t. I can make this vector using only one function and some other vector of constants. And that leads us immediately to an assumed form that our x non-homogeneous is going to be an e to the 2t times u1 and u2. This is a two-element vector. Our solution should be a two-element vector as well. Then what do we do next? Well, we sub in our x non-homogeneous and we solve for u1, u2. Or if you like, we'll keep it as a vector when we first get started and then hone in on u1, u2. So to sub this in, we're going to take our differential equation all the way down here. We're going to do it as we go because we have enough familiarity here. The derivative of e to the 2t is going to be 2e to the 2t times our vector u. that's going to equal our 6 minus 7, 1 minus 2, x again, so e to the 2t, times u1, u2, plus, we're going to bring the function out so it's easier to see, and that leaves just the 10 and the 0 as coefficients. And the nice thing at this stage is we can divide through by e to the 2t. Every term has one, and it's never 0, so we can divide through by it quite safely. Now we get into the solving equations part. So let's write this out as matrices here in vectors. 2u's is 2u1s and 2u2s. Here we're going to have 6u1 minus 7u2, and here we're going to have u1 minus 2u2s plus 10 and 0. And however you want to solve this kind of thing is up to you, but we get two linear equations, two unknowns. I like to keep the constants on this side and then bring everything else over. So we have the two equations. We'll have minus 4u1 plus 7u2s. The second term is 2u2 plus 2u2, so it's 4u2s, and minus u1s. And that's going to equal 10 and 0. We could write it in actual vector notation, matrix vector system here. We've got this times u1, u2 now is equal to 10 and 0. Well, what do we do with that? We can do row operations. We can do 1 minus 4 times the second equation here, and that will give us, we'll put the first one first because it's nicer, negative 1, 4, and then this minus 4 times this will be 0. This minus 16 will be minus 9, u1 and u2, and that will equal 0. On the top is our first equation, and then this minus 4 times that, so that's going to be 10 again. Having done that, we end up solving and getting minus 9u2 is equal to 10, so u2 is equal to minus 10 ninths, or around minus 1.11, etc. Having found u2, we can then back solve for u1. We'll do that on the next page. We found u2 is minus 10 ninths, so we can then proceed and say that minus u1 plus 4 u2s is equal to 0. So u1, bring that over, it's negative 4, but that's negative 2, so we have 4 u2s, and so that's negative 40 over 9, 4 times that. So what we get is our non-homogeneous solution is equal to the differential family we said was e to the 2t, so we'll have an e to the 2t, but the particular vector that goes with that, the undetermined coefficient, is going to be u1, negative 40 over 9, and u2, negative 10 over 9, or if we want to tidy that a bit more, we can say e to the 2t times 10 ninths and negative 4, negative 1. And that is the method of undetermined coefficients for matrix forms of first-order systems. The last step would be to find our general solution, and that would simply be what we found for the corresponding equation, that collection of things, plus the part that comes from the non-homogeneous that we just found now, that would go in there.